We've seen so far how it's relatively easy to convert a regex into a non-deterministic finite automata, but non-determinism is sort of awkward to work with, so it would be nice if there was an algorithm that converted regexes straight into deterministic finite automata. And it turns out that there are a bunch of algorithms that do this, but we don't use basically any of them, and this made me quite curious. This video is now about why we don't use them, so there's going to be a lot of bad algorithms in this video, as well as a bunch of random Unix history that I just can't get my head out for some reason. We're going to start off by looking at the way that you can convert non-deterministic finite automata to deterministic finite automata. I also, in an attempt to keep the running time of this video down, tried to get myself as often as possible to say DFA and NFA rather than deterministic finite automata and non-deterministic finite automata. You will be able to see how well that went. Now, there is actually a fairly straightforward algorithm to convert an NFA or non-deterministic finite automaton to a DFA or a deterministic finite automaton, and it's called the power set construction. It was first put forward by Michael Rabin and Dana Scott in 1959, actually at the same time that they invented NFAs, which they won a Turing Award for, by the way, though if you throw a rock in this video, you're going to hit a Turing Award winner, so I'm going to skip mentioning all of those Turing Awards, lest this just become a video about who won a Turing Award. The algorithm works like this. Consider this regex and this matching NFA. We're going to start off by activating the start state, and then we're going to compute the epsilon closure, which means we follow all of the epsilon transitions, which means any transition that doesn't directly consume a character. Those are annotated with these funny little e's, the epsilon symbol. At the end of this process, you have the states S, 1, 4, and F activated. And our first state in our DFA is going to be the set of all of those active states. Since it involves taking a subset of the NFA, this algorithm is also sometimes called the subset construction. The simplest form of this algorithm actually works by looking at all of the possible subsets of the NFA, which is called the power set. But since we know where we're going to start, we can narrow it down quite a bit for our purposes and just focus on the useful states. Next, we ask the question, in this state, what symbols can the NFA accept? And in this state, we have two transitions possible, both of which only accept the symbol B. So our DFA is going to need a B transition out of this state. And now we need to ask the question, what states are going to be active if this NFA accepts a B symbol? And in this case, it's only 2 and 5, which become the next state in our DFA. And we ask the question again, what symbols can the NFA accept from this state? And the answer is one of two symbols, A or B. So we're going to need to have two transitions out of this state in our DFA, one for A and one for B. Now we ask the question, what if we give it an A? In that case, then the state 3 will activate. But we're also going to have to compute the epsilon closure again every time we accept a character. So we're going to have to activate F, S, 1, and 4 as well. So the next state for our DFA is going to be 3F, S, 1, and 4. And we then follow the same logic for the B transition going downwards. Here things can start to feel a bit messy with us keeping track of where we are in the NFA, and the thing to realize is that we don't need to keep track of where we are in the NFA at all. We just need to look at the new DFA states that have been generated, but which we haven't looked at yet. For each of those, we need to ask ourselves, if all of these states were active, what symbols could the NFA accept? And then what will be the states after that. So to explore the upper right DFA state, let's activate 3F, S, 1, and 4. If you look at all of the transitions out of these states, you will notice that we can only accept a B symbol. And actually, if we evaluate the states that will come after that, you will see that it's only 2 and 5, and we already have that state in our DFA. And we don't need to duplicate it, we can just create a transition back to the 2-5 state we've already got. We perform the same logic with the 6F, S1, 4 state and get the same result, a B transition back to 2-5. And now there aren't any unexplored transitions left, and so we're done. All we need to do now is work out which of the states are accepting. And the rule is quite simple. If the DFA state has the matching NFA state in it, that's the F here, then it will be accepting. And here's our DFA. But many people have thought, this business of creating an NFA and then converting it to a DFA feels a bit unnecessary, and it certainly takes extra time, maybe more time than it would take to use the NFA directly. So it would be pretty nice if there was a way of creating a DFA from a regex directly without this NFA intermediary step. And that's what this video is going to cover. A few of the ways that people have tried to do this. There are many different algorithms, and I'm not going to try and cover them all, and I'm also not going to be capital R rigorous about it. I'll just give you the general idea of how they work. I got curious about this subject because the last regex video I made, I noted that the Thompson construction, which is the most popular algorithm to create an NFA from a regex, is also sometimes known as the McNaughton Yamada Thompson algorithm. The Japanese Hisao Yamada, at the time a graduate student at the University of Pennsylvania, worked with his professor Robert McNaughton in developing and publishing an algorithm which could convert regular expressions to finite automata. We must assume that whoever wanted to name it this thought that Robert McNaughton and Hisao Yamada had contributed something important to the algorithm that Ken Thompson describes in his paper, despite the fact that Thompson didn't reference them at all. I suspected at the time that something somewhat strange was going on because their algorithm is a little different to Thompson's algorithm. In fact, their algorithm in some ways is better. I believe it goes directly from regular expressions to deterministic finite automata, and so in theory would be more efficient. However, I haven't actually managed to get a hold of the original paper, which is called Regular Expressions and State Graphs for Automata. So if you can help me out, let me know. Many kind people then sent me the paper, and so I've had a chance to take a look at it. And I was right. It's quite a different algorithm. And it does in fact convert regexes into DFAs. It was also published quite a bit earlier than Thompson's work, and it was very well known, being cited in most of the comparable papers around that time. So why didn't it catch on? And to explain that, I'm going to take you through some of the history and then through how their algorithm works. Now, regexes come out of the theory of computation, so there's a lot of theory. One place we can trace it back to is the early theory of neural networks by Warren McCulloch and Walter Pitts in the early 1940s. Now, this era of computing is really fascinating because today, if I said to you that we're going to create artificial human-like intelligence, you might think this is either wild hypemanship or an absolute inevitability, but you probably agree with me that lots of people think that this has nothing to do with the field of computer science. That serious thinkers take the view that computers are calculating machines, fundamentally incapable of human-like thought. And I wouldn't be surprised if you thought that the early computing pioneers felt the same, that they were serious, by-the-numbers technical people concerned with calculation, not creating life. But that is not true. Many of the early computing pioneers felt that they were working towards creating a thinking machine, artificial life. Here is McCulloch himself talking about this.
Somehow the purpose that a machine, no matter how complicated and how clever, could have, to my mind, isn't equatable. When man has gone, these machines would in essence be purposeless.
I doubt that. I would say in essence they would be purposeful.
And there would be, in your feeling, nothing gone and nothing missing from the world.
Well, you mean in the sense in which the dinosaurs are missing?
No, I mean in the sense of something important.
Well, aren't they important? Weren't they important? I mean, there's one thing you could be pretty sure of: man won't survive forever. From all that we know of the sun and of other stars, that would be the most improbable thing. Something else will come.
And in your opinion, it might be something of man's own creation?
Yes.
I find his intensity here absolutely captivating. It's exciting to think that not even 100 years later, the descendants of his theory can now talk to us directly. And one of the other descendants of his work is regular expressions. It actually makes me smile to think of regular expressions as tiny baby versions of LLMs. They're both pattern recognition machines, and regexes are like the cute little versions who can find tiny patterns, whereas LLMs are the huge, mysterious versions who can do who knows what. So anyway, McCulloch and Pitts introduced the idea of the neural network in this wonderfully titled paper, A Logical Calculus of Ideas Immanent in Nervous Activity. Stephen Claney then built on their ideas, along with some ideas from Turing, to write Representation of Events in Nerve Nets and Finite Automata. And it was Claney who developed regular expressions. They're called regular expressions, by the way, because to Claney they were about recognizing patterns of events in time that happened more or less regularly. This, of course, is quite an important thing to do if you're trying to create intelligent behavior. In fact, one way, not necessarily the best way, but one way of thinking about intelligence is the ability to recognize patterns and then respond to them correctly. In the late 50s, Claney's ideas were given a boost by a trio of authors: Irving Copy, Calvin Elgert, and Jesse Wright. They wanted to reformulate Kleini's ideas in a way that would make more sense to a wider audience, and so they refined them and introduced some alternative notation. All of this, though, still is about events in time, not strings of characters. That comes much later. Quickly after this, there are two divergent paths. The first is Michael Rabin and Dana Scott, who, in their paper Finite Automata and Their Decision Problems, invent non-deterministic finite automata, or NFAs, and later win another Turing Award for it. But I said I wouldn't mention that, so that's enough Turing Awards for today. The other path is the paper I mentioned earlier, Regular Expressions in State Graphs for Automata by McNaughton and Yamada. They have a big advantage when it comes to inventing an algorithm to construct DFAs because they very probably don't know about NFAs yet. McNaughton and Yamada were writing their paper before Dana and Scott had published on NFAs, and so they really had no choice other than to think in terms of determinism. We'll look at their algorithm through an example based on the example they use in their paper. We have a regex here which consists of 1A and then a group of either BB or BA, and that group can be repeated 0 or more times, followed by a final B. In computing, we don't often think about the alphabet of a regex because we assume it's just any character. But at the time, they weren't necessarily thinking in terms of string matching, and so the alphabet was more in the foreground. This regex's alphabet consists of two symbols, A and B. In the paper, they actually use 0 and 1 here, but I thought that would be too confusing, so A and B it is. The first thing we need to do is to enumerate the positions in the regex. In their terms, a position is a symbol in the alphabet. In Chomsky grammar terms, these are the terminal symbols, the symbols that actually appear in the string to be matched. And in finite automata terms, these are going to be the positions that actually consume a character. So we give each of these positions a number, in this case the numbers 1 through 6. Then we're going to go through each position and work out which positions could possibly come next. So if we had consumed an A symbol, and so we were in position 1, the next positions could either be the B in position 2, the B in position 4, or the B in position 6. I'm going to write these down on the right hand side as we go. We go through each position in the regex, writing down the transitions out of each position and what they're going to be transitioning to. This one, position 3, is a little trickier. We could exit the group and land on position 6, or because of the star, we might repeat the group again. If we do that, we're going to end up on one of the two positions which start that group, the B in position 2 or the B in position 4. The rest are broadly similar to what we've seen so far. Here's our final table. This table tells us, for each position, what positions could come next in the regex. This part, which we'll call phase 1, isn't actually strictly necessary. You could do phase 2 without it, but it makes it a little easier to understand what's happening. In phase 2, we're going to go through the pattern slightly differently. We'll start off by activating the position to the left of the first position. We'll call that S for start. We then ask this question. For every symbol in our alphabet, what positions would be active next if we saw that symbol? For S, the answer is simple. If we see an A, we'll activate position 1. We start to build up the states in our DFA in this way. We'll be exploring the DFA state by state, so I've marked the unexplored states with dashes to indicate that we'll explore them next. If we see a B, however, we've got no match, so we transition into a non-matching state, which I'll put in red and call no. Next, we explore state 1. We ask, what if position 1 is active and we see a B symbol? And the answer is that 3 positions could be active, 2, 4, or 6. So just like in the power set construction, our set of positions is 2, 4, and 6, and that's set as our next state. And if we get an A symbol, then we transition into the reject state. Next, we explore state 2, 4, 6, and for this we have to ask again, what positions would be active next if we saw a B? If so, position 2 would transition to position 3. The other possibilities would die, but we don't mark those out as rejections because we still have other possibilities alive, and so the match as a whole is still going. If we saw an A, position 4 would transition to position 5, and so we mark that out too. We've also got the end state to deal with, where we're on position 6. And our rule can be that if we have the last position active in our state, that's state 6, then we can mark that as a matching state. This logic may be easier to imagine if you think of this regex having an invisible end of string symbol which we matched if seen. And that's our state 246 fully explored. Next, we deal with the state where just 3 is active. If we see a B symbol, position 3 will transition into either 2, 4, or 6, and we already have that state in the DFA, so we just point back to it. If we see an A symbol, we transition into the non-matching state. And for the state where just position 5 is active, we have a similar result. And that's it, our full deterministic finite automata constructed. This construction is very nice, but there is a glaring problem with it. How do you come up with that list of next positions in the first place? Their paper doesn't seem to mention it at all, and I've not found anything that solves this problem in any literature they've cited. I may have missed something, and perhaps it was so well known that they didn't feel the need to mention it, but it's also possible that they weren't really working with computers very much, and they just meat-brained it out. So it's good, I don't hate it, it just isn't really programmable yet. In any case, all of the previous theory I've mentioned then gets studied by somebody called Janusz Brzozowski. In 1964, he invents a rather fascinating process for evaluating regular expressions, which is now called Brzozowski derivative. You can use Brzozowski derivatives for a bunch of different things, but we're going to use them to create a regex evaluator. This involves repeatedly applying a process called taking the Brzozowski derivative, and if we end up without any regex left at the end, or something which could be an empty string, then we've got a match. So, what is a Brzozowski derivative? It's essentially the process of working out what a regex will be after we process a specific symbol. So in this case, where we have the regex ABC, if we process the symbol A, we're going to be left with BC. If we were to process a different symbol like C, then we wouldn't have a match. And a bit like derivatives in calculus, there are a set of rules that we can apply. Evaluating a regex then becomes a bit like the process of solving a mathematical equation. To illustrate this, I'm going to use this notation that I made up. That little d means derivative, and the braces surround the regex to be derivatated, and the letter in the arrow is the symbol we're going to derive with respect to. That means we want to get the regex after we've seen that specific symbol. Let's work through a couple of examples which will illustrate the rules on the right. Firstly, we'll look at a simple string of characters to match. You might think that the first rule we have to use is rule 1, but it's actually technically rule 3. If you look at this regex like an expression, it consists of two literal characters, x and p, wrapped in a concatenation operation. So we need to apply the concatenation rule first. This rule has two possible paths depending on whether the first item is what's called nullable. Nullable means, could it possibly be an empty string? And in this case, the answer is no. So we use the second part of the rule. So let's substitute this rule into the expression. Now we can apply rule 1, which tells us that the derivative of a single character with respect to the same character is an epsilon, and the epsilon is just an empty string. At each step, we can also simplify the expression to make it shorter and easier to process. We don't strictly need to do this for the algorithm to work, but it definitely makes it easier to follow and faster to compute. In this case, that just means we can get rid of the epsilon, because an epsilon concatenated with anything is just that second thing. We can then take the derivative again with the second character in our string, and this gets us our final result, just an epsilon. To work out if our final result is a match or not, we ask whether it is nullable, that is, whether it could be an empty string, and in this case it definitely is an empty string, so we have a match. Let's look at another example, and in this case our example is going to have a union in it. That's what that bar means, and it's going to be a union between A, B and AA, meaning the result could be either AB or AA. And in this example, the first rule we want to apply is the rule for union, rule 4. This rule tells us that the derivative of a union is the same as a union of the derivative of the left and the derivative of the right side. After this, we apply rule 3 again to break down the concatenation, and then rule 1 to resolve both to epsilons, which we can then simplify out. We've now processed the first character, so we move on to the second character, which is also a v. We apply the same rules as before, but this time the right side ends up as a null symbol. That's that circle with a line through it, which is used in mathematics to mean the empty set. What this means is that there are no valid matches on the right-hand side. This is fine for our match as long as it's not the only symbol left. As it is, we simplify it out and end up with an epsilon at the end, meaning we have a match. We've just got two more things to look at, the Kleene star and what happens if we get a nullable item in a union. Let's look at them together. Before we dig in, have a think. What do you think the derivative of this regex should be for the character A? The answer is sort of amusing. I think it's amusing anyway. First, we need to apply the concatenation rule, rule 3. Our first item in this case is A star and our second item is HA, which itself is a concatenation. According to this rule, we need to check whether the first item is nullable. And Kleene stars are always nullable because they might possibly be 0 repetitions and therefore could match an empty string. What this means practically is that we can't be sure whether the derivative should apply to the first or second items, since the first might be empty. As such, the derivative of a nullable item concatenated with another item is the union of the two possibilities. The first possibility is that the first item ends up being non-empty, and so we take the derivative of that and leave the second item alone. And the second possibility is that the first item ends up being empty, and so we discard it and instead take the derivative of the second item. Having done that, we now need to apply rule 5 to get the derivative of A star. And this one I think is actually really neat. To get the derivative of the Kleene star, we take the derivative of its item and then leave the starred item on the end. And this is kind of equivalent to unrolling just one of the repetitions. Let's see how that plays out. We can then apply the rules we've seen before to take the derivative of HA and then the derivative of each individual character. Then we have a union where on the left we have an epsilon and then our original regex, and on the right we have an empty set concatenated with an A. The empty set concatenated with anything is just empty again, so we can simplify away that side of the union. Likewise with the epsilon, which gives us our original regex, which I think makes sense. If that A star HA regex absorbs one A, it's not going to be changed by it because it's still going to have to be prepared to absorb another A if necessary. And we do this again with the second A character in our input, but since we've already calculated it, we don't need to do it again, so we can skip all that work. Then we've got our H character to deal with. We apply the same rules again to take the derivative with respect to H, except this time our empty set ends up on the left and our valid match ends up on the right. The A star and the H are thus chopped out. And then we absorb our final A character, which is trivial and results in a successful match. There are a couple other details to this algorithm, like how do we tell whether something is nullable, and since that is our test for if we've got a successful match, that's quite an important question. And there's a set of rules, but I'll let you puzzle them out for yourself. They're quite intuitive if you just think of it as trying to work out whether a given term could ever match an empty string. Put your answers in the comments if you like. This is very cool. Evaluating regular expressions in this way is quite simple, and it's probably now my favourite way to write an evaluator. I love how all of the ideas are very simple, and if you forget the rules, you could probably quite easily rederive them if you just thought about it for a bit. And there's not much to get wrong. In terms of efficiency though, they don't seem like an obvious winner. You'll need to reprocess perhaps the whole expression on every symbol, and the expressions could get quite large. You could instead build a DFA by following a process similar to the power set construction to go through the expression, ask which symbols could be accepted each round, and what the resultant expressions would be. But this can also become problematic. In modern regexes, we're used to dealing with lots of symbols since we're thinking about characters rather than events in time. And in order to tell whether we should add a transition back to a state we've already seen, we'll need a way to tell whether a regular expression is the same as another one, which is possible but kind of complicated. I suspect these problems combine to make Brzozowski derivatives a bit of a hassle for production purposes, but there has actually been a modern revival. In 2008, Scott Owens, John Reppy and Aaron Turon wrote a great paper titled Regular Expression Derivatives Re-examined, which makes the case for the Brzozowski technique, particularly in functional languages, and there have been some modern developments too which make the technique a bit simpler to apply. Search up Antimirov derivatives if you're curious. I couldn't find a pronunciation reference on that one, so I hope I got it at least ballpark correct. In 1986, Ken Thompson publishes a regular expression search algorithm. Actually, it's just regular expression search algorithm, but it's just so annoying to say. He describes an algorithm very close to the Thompson construction algorithm that we covered in the last couple regex videos. At the start of his paper, he states, in the terms of Brzozowski, this algorithm continually takes the left derivative of the given regular expression with respect to the text to be searched. And of course he cites Brzozowski's paper too. Russ Cox, who wrote a great series of articles I used a lot for my regex videos, actually wrote that Thompson learned about regular expressions directly from Brzozowski at Berkeley while Brzozowski was teaching there for a semester. I found one other source for this, but no definitive proof. Still, the way Thompson describes his algorithm does make it seem like it was based on a lot of valuable conversations with Brzozowski rather than, for example, Thompson reading all the major papers on the topic. You can see, for example, the influence of McNaughton and Yamada's work, but more as if it was distilled via a third party rather than a direct build. That's a guess, of course. I don't know exactly what happened in every moment of Ken Thompson's life. Thompson's construction is frequently described as an algorithm to convert a regular expression into a non-deterministic finite automata. However, some, including Russ Cox, have pointed out that his paper does not actually mention NFAs. If you gloss it, you can be like, yeah, little circles with arrows, states and transitions, it's all fine. But if you look a bit closer, this isn't the finite automata notation we're used to. It will of course have to be equivalent in some way, but notice that the squectangles aren't actually states, but instead processes that consume characters. And the arrows aren't labelled like for transitions, but there are some sort of special splitting nodes which do the explicit job of splitting some kind of signal. Lines also just join together, but it's not a classic state transition finite automata diagram we're used to. You could probably translate these pretty directly to NFA, but it doesn't seem like he's building on the work of Rabin and Scott here. And at least when it comes to finite automata, he cites only Brzozowski and Kleene. To me, Thompson's diagrams look more like these diagrams from Realization of Events by Logical Nets by Copy, Elgert and Wright. And we know that Brzozowski would have known about these since he cites them in his own work, and so perhaps Thompson was building off of that second-hand. So what I suspect is that Thompson, as an engineering type working with scientists, spent quite a lot of time with them, absorbed their ideas, and just started using them to build things. And he then eventually wrote some papers about what he'd done. His work is definitely building on the work of Brzozowski, McNaughton, Yamada, Rabin and Scott, but the attitude is more like, my primary job is creating Unix, not crafting theory. In his paper, he also describes what I've called the lockstep algorithm, which simulates the NFA character by character rather than using backtracking. This is actually quite similar to performing the power set construction on the fly, and this is a very nice algorithm, but in keeping with Thompson's pragmatic character, he later discards it in favour of a backtracking approach in some of the early Unix tools like ed and grep, where I guess backtracking looked like the simpler approach to implement. This technical decision was later locked in, perhaps by an unfortunate series of events which I speculated on in an earlier video. And as a side note, the video I put down to make this one is actually on Ed, the text editor, and as a result I've been reading quite a bit of what's probably Ken Thompson's code, which I think has given me just a little insight into the way that he thought, so these guesses as to how he was thinking are informed by that too. But he had a colleague, Alfred Aho, who was much more theoretically minded, and in 1975 Aho wrote a tool called egrep, which is quite similar to Thompson's grep but with some extra regex features, and it also uses the lockstep algorithm. Now this is purely speculation, and I've watched a few interviews with Alfred Aho now and he never really gives this impression. But consider if you were working at a tech company and you had a good product and there was an existing tool which worked reasonably well, but you thought it could be significantly improved. What sort of mindset or situation would drive you to create your own competing tool instead of implementing improvements to the existing tool? It's possible that this was just because Aho knew that since back references had recently been introduced to vanilla grep, back references which then forced the implementation to use an inefficient backtracking approach rather than the lockstep algorithm that he knew was better, that he would need to create an alternative tool in order to ensure backwards compatibility wasn't broken. But what it seems to me is that it gives like a vibe that he's thinking this program grep is kind of misguided and I'm pretty sure I can do it better, but I don't really want the hassle of trying to persuade Ken Thompson and his teammates that this other way is better. So I'll just write my own and maybe it'll catch on. And I've definitely been in that position as well. And what's added to my interpretation here is that Aho famously wrote egrep over a single weekend, and I've definitely had the fantasy of re-implementing one of the core products of my company in a single weekend before. I guess the difference is Alfred Aho actually did it. Regardless of how true all that is, along the way Aho seems to somewhat play with the threads of history. He would later go on to be one of the co-authors of the Dragon Book, also known as Compilers, Principles, Techniques and Tools. I don't mind going out on a limb here and saying that since Aho did so much work in pattern recognition and regexes, that he probably wrote the bulk of its chapter on regular expressions of finite automata. And in that chapter he sort of seems to massage Thompson's original algorithm to make it fit the theory. For example, he presents it as an algorithm to construct a non-deterministic finite automata using epsilon transitions rather than Thompson's original splitter circuit type explanation. Now, if you're writing one of the premier undergrad computer science textbooks, this is exactly what you would want to do. Tie all of the various ideas together into one coherent story that makes sense to students, rather than the messy stepping back and forth that really happens. How McNaughton and Yamada get into the matter is less clear. Their work is very important, but it honestly doesn't seem like they describe anything to do with Thompson's construction. Aho, or possibly his collaborators, seem to start attributing this algorithm fully or partly to McNaughton and Yamada around 1992. It's sort of odd. For better or worse, Aho also routinely writes himself out of these stories, and maybe that's noble, but it also leads to a sort of maddening research process where everything seems to come back to Alfred Aho. Either he invented it, or he massaged it, or he has his fingers in it in some other way. I'd almost prefer it if he wrote, "Listen, Ken Thompson, he's a great guy and all, but his algorithm needed some work, and it was me who had to step forward and do it." See, I'm always the one who has to bail these engineering types out with a spot of finely tuned theory. It's rare that I wish programmers would have a little more ego, but I guess there's always a first time. Anyway, when writing egrep and awk, Aho couldn't resist having a crack at going straight from regexes to deterministic finite automata, and that's the final algorithm I'm going to walk you through. He doesn't name it after himself, of course. In fact, it doesn't really have a clear name. Now, I assume if you've got this far, then you're okay watching laborious worked examples of different algorithms, but this one is going to challenge you even more because it's a true monster. After some study though, I think I can make it make sense. The basic idea is to fill in the missing piece of the McNaughton Yamada algorithm by working out which positions can possibly come next after other positions. We do this by somehow constructing a syntax tree, it doesn't really matter how, and then working through the tree bottom up while applying some rules based on the type of term that we're dealing with. Now, I actually think the tree format actually makes it a bit harder to understand, so I'm going to diagram it out slightly differently. This is the same regex as before, just in a nested structure. In blue, we have all of these symbols in our alphabet as they appear in the pattern. And just like in the McNaughton Yamada algorithm we saw earlier, we've labelled them with positions. Each of these containers represents an operation in the regex. We have concatenation, which is invisible in the expression but still very important. We've got the union, which is usually represented by the vertical bar, and the Kleene star with the asterisk. Note that this algorithm also requires us to add a special symbol on the end, which represents the end of the pattern and the matching state. And we're going to use the hash symbol for that, or the pound sign if you like. The first phase of this algorithm is to calculate three things for each box. The first of those things is nullable, which is the same as we saw in the Brzozowski derivatives. The other two are first pos and last pos. First pos is the set of positions in the box that could match first, and last pos is the set of positions in the box that could match last. If that doesn't make much sense yet, it's okay, we're going to work it through in laborious detail. Each of the actual symbols, those blue boxes, are trivial. Their first pos is their own position, and their last pos is also their own position, and none of them can be nullable because they're only ever going to match that symbol. So next we'll move to this concat on the left, which I'll highlight in yellow. Firstly, is it nullable? It is not, because it's only ever going to match BB, and it can't possibly match the empty string. And we'll notate this by giving it a big strong arm emoji to show that it's going to take up space. Now, let's say that this concat item matched something. What positions could possibly come first? Only position 2. That's always going to be the one that comes first, so we'll put 2 in the top left. Finally, what positions could possibly come last? Only position 3, for the same reason. It's always going to end in that position 3B. The logic for the other concat is the same. As we go through, I'll mark the ones we've done in green to keep the yellow focused on the one we're looking at. Next, we'll need to tackle this union. Is it nullable? Well, the rule for this is that if either of the union's children are nullable, then it could also be nullable. Since neither of those children, the two concats, are nullable, then it's not nullable either, and so we can give it the strong arm as well. For first pos, the question is, what is the set of all positions that could come first if this term matched? And the answer is that either 2 or 4 could possibly come first. So first pos is going to be a set of 2 and 4. For last pos, the question is, what is the set of all positions that could come last if this term matched? And the answer in this case is 3 or 5. So last pos is a set of 3 and 5. Now let's look at the Kleene star, representing an item that could be repeated 0 or more times. Now a Kleene star is always nullable because it might be skipped or repeated 0 times. So we'll put this little ghost emoji here to indicate that it's sort of ethereal, may or may not be there. As for first pos and last pos, we could just stare at it and try and work it out, but there is a rule. For a star node, the first pos is always going to be the first pos of its child, and the last pos is always going to be the last pos of its child. I mean, there aren't really any other options, so it's got to be those. These next concats are a little more complex than the ones we've seen so far. The rule for nullable with concat is that if both of its children are nullable, then it's also nullable. Otherwise, it's not nullable. So it's equivalent to taking the logical AND. In this case, the A symbol is clearly not nullable, so our concat node isn't nullable either. The rule for first pos is that if the left node is nullable, then we have to take the union of the first pos of its left and right nodes. However, this left node is not nullable, so we just take the first pos of the left node, which is 1. That sounds more complicated than it is. The idea is that if this concat node matches, then its first position can only ever be that A at position 1. It has no way to skip past that because it's not nullable, i.e. it can't be empty. If it was nullable or could be empty, then we wouldn't know whether it was going to land in the first part of the concat or the second, because the first part could be empty and we could land up in the second. So we need to take the union of the first positions of both children. The rule for last pos is the same but inverted. If the right node is nullable, then we have to take the union of the last pos of the left and the last pos of the right nodes. That ghost should remind us that the right node is nullable, and so we take the union of the last pos of both our left and our right nodes, so 1, 3 or 5. Intuitively, this should also make some sense. The possibilities for this node is that it could end up being A with 0 repeats of the group, in which case the last position would be 1, or it could repeat 1 or more times, in which case the last positions could be the last character in either of those unions, that's position 3 or position 5. The logic for this next concat is a bit simpler because both of its children are non-nullable, so it's not nullable either, and we take the first pos of its left child and the last pos of its right child. And the only unusual thing about the topmost parent, the root node, is that it has this hash ending symbol in it. Otherwise, all the rules are the same. It's not nullable, and for first pos we take the first pos of its left node and the last pos of its right node. When I was recording this, I was second guessing myself because I don't know why I'm using past tense, it's literally right now, but this hash ending symbol, is that supposed to be some sort of 0 width ending symbol? And as far as I can tell from the description of the Dragon Book, it's not. It's just an ordinary symbol that we should treat as an ordinary non-nullable symbol. But I don't think it makes any difference, but you may have a different opinion on that. Let me know if you find anything out. And that's nullable, first pos, and last pos calculated everywhere, which is nice, but all of this was so that we could calculate another value for every blue square. Followpos. Followpos is the set of positions that can follow a given position in the regex, and it doesn't apply to all of these nodes, it only applies to each of these symbol positions here labelled 1, 2, 3, 4, 5, 6 and 7. But we calculate it by going through each of these grey boxes, and actually not all of them, only the concat nodes and the star nodes. I've also shifted our diagram around just a little bit to make space for us to put the followpos numbers right below the blue boxes. Let's build it up. We'll go through all of the concat nodes first, starting at the root node. The rule for concat nodes is described in the Dragon Book like this. If n is a cat node with a left child C1 and a right child C2, then for every position I in C1's last pos, all positions in C2's first pos are in I's followpos. To put it another way, if this concat looks at its two children, it knows that the last positions of its left child can be followed by the first positions of its right child. So we know that the followpos of position 6 must contain position 7, so we mark that down. We can now move on to our next concat node. For this concat node, we know that for each of the final positions of its left node, they could be followed by the first positions of its right node. We write those down under each of the 1, 3 and 5 boxes. Another way to put this is that if we're on, say, position 5, that's that A there, the concat node tells us that we might next visit position 6, because the concat node is telling us that this has to come after this. We move on to the next concat node, and this one tells us that for each position our left child's last pos, that's 1 itself, it might be followed by any of the items in its right child's first pos, that's 2 or 4, and we write those down too. We have our other two concats to do, but these are pretty trivial. 3 is going to come after 2, and 5 is going to come after 4. That's all our concat nodes processed, but there's another kind of node we have to look at too, the Claney star. The rule for a Claney star is written in the Dragon Book like this. If n is a star node and I is a position in n's last pos, then all positions in n's first pos are in i's followpos. To put that another way, If a star node looks at its single child, all of that child's last positions could be followed by that child's first positions. For example, in the case that it looped back around to the start. That's not exclusive, it could move out, but we've already handled that in our concat nodes elsewhere in our processing. So we go through the positions in our star node's last pos and add each one to all of the positions in our star node's first pos. And schwupp-de-whoop, we have our follow pos for every position. From here, we could use a variety of methods to get a DFA. Something like the McNaughton Yamada construction will work just fine. We need to start off with the first pos of the root node, which is 1. Then we build up using the follow pos segmented by the symbol of the node we're transitioning to. Since 6, 2, and 4 are all B positions, we just put in one transition to a state representing the set of 6, 2, and 4. From there, we look at each of those positions given an A or a B, and we get this. We also have a state that transitions to the end of the string, which we could mark with this hash or just mark the 624 state as accepting. Either is fine. Finally, we explore the states 5 and 3 to see that they transition back to 624 again. And this, of course, is essentially the same thing we got with our McNaughton Yamada algorithm. I assume that Alfred Aho had perhaps read their work, noticed that it had this gap in it, and then tried to fill in the gap with this algorithm. Now, when I was working on this video, I also tried to invent something that would make the McNaughton Yamada algorithm work. That's before I studied this algorithm. And so I was essentially trying to solve a similar problem to that Alfred Aho was, but with much more advanced tools. And as a result, I can really appreciate that a lot of ingenuity went into this algorithm, and I imagine that was the product of much careful study. However, there is this one clip where Aho recounts Kernighan's reaction to what I believe was probably this algorithm as it was encoded in awk, and I believe that because the Dragon book talks about his using it in awk, and this is around the right time. And I think Kernighan's reaction illustrates pretty well my feelings about it.
I actually wrote the pattern matching algorithms that are in awk, and Kernighan decided that it needed more comments on it, because you should comment your code, and his comment was, "Abandon hope, all ye who enter here." That's what he thought about my algorithm. He said it was too complicated for a mortal to understand.
So possibly because of this, egrep actually switched to using Thompson's construction later, simulating the NFA, and then using some caching as well to try to speed it up, which is where most implementations sit today. It seems that nobody really found a particularly good way to convert regexes straight into deterministic finite automata, at least not without sacrificing significant complexity or functionality or some other such thing that we might want. It seems like simplicity combined with functionality has won the day again, and I doubt it'll be the last time that I say that. As always, there's some homework for you if you'd like to try some of this stuff out yourself, and this time it's to create a regex evaluator using the Brzozowski derivatives. They're super fun to build, pretty simple, and pretty cool to be able to say you can build your own regex evaluator using Brzozowski derivatives pretty quickly. These videos are supported by the ODES membership scheme, which you can find on the ODES website linked in the description, which is also where you'll find loads of resources and papers that I read for this video, as well as the exercises that I mentioned. If you'd like to sign up and support the project, you'll get an extra exercise with every video, including this one, which is a bit of a build on the Brzozowski derivative exercise 1, as well as ad-free viewing and a few other things which you can find on the ODES website. If you click the link in the description, click all the buttons, and you'll get to the right place. Also, thank you to those people who support me to make these videos through the membership. I really appreciate you. That's it for this video. The next one should be something a bit special. It's going to be related to text editing and linked lists and a few other things. And there'll be a bunch of Ken Thompson in it as well for all those Ken Thompson fans out there. See you soon and have a great day. Oh, and also I've been slouching too much, so I just want to show you the geese on this jumper. I just felt you should see. That's all. Goodbye.